Hi, welcome to another lecture of Physics 2101. So in the previous lecture we finished chapter 8 and then we had a revision lecture which I hope was useful to most of you at least, if not all of you. And today we're going to move on with the syllabus to chapter 9, in which we are going to be speaking at the beginning about the center of mass and linear momentum. Let's start. Center of mass. What is center of mass? Well, in a way we have been using the center of mass without actually knowing that we have been using it for quite some time now. Say for example when we were doing calculations in chapter 3 or chapter 2 about a ball jumping up and down, or a human being falling, or an elevator going up, or whatever you want to call it. Every single time we never actually drew a full person in a free body diagram, did we? We simply used one dot, one point, and we acted as if all the forces go in that point. Okay, take me as a person. Where is that point in me? And why is it even okay to represent something that is, about 1.5 meters by a meter by just a simple dot? And more importantly, why does the physics still work? This is something very, very unusual. Usually if you represent something with something else, it doesn't work. It just simply stops functioning. But here we have been doing this all along without even noticing that it's an issue. Why? Well, the answer is something called the center of mass. And what this is it utilizes a phenomenon in physics where we act as if everything is centered at a single point in a solid body, and things still work out. Let's take a look. Let's take this cube that's in front of us, and then let's look at a cross section of it, just a square. Now if I just gave you something, a piece of something like that, okay, and I told you, okay, where is the center of this piece? Without even thinking, you're going to point right at the center and say this. Fine. Why? Well, some of you who might be interested in balancing stuff would notice that by simply placing my finger at the right point here in the center, I could probably balance this whole thing. Okay? So what am I doing? I am utilizing the fact that when the density of something is uniform all along, all around, it has a point where there is exactly the same amount of mass on top, on bottom, left, right, up, down. Okay, and that's what we call a center of mass. Let's now take a look at the same exact thing, but in 3D. Okay. If we take it in 3D, where is it going to be? Well, if I take this center of each square and then put them all on top of each other, it's going to be a dot right in the middle of the cube. Correct? Good. Why is this thing not moving? Okay. Let's take something a bit more complicated. Say, for example, a baseball bat. Now, this is obviously not a symmetrical object. It's heavier on one side, lighter on the other. So when I throw it, it's going to go in a weird way, something like this. It's going to rotate, 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 and go all the way down. Now, one would say it's impossible. It's not like a ball. A ball is very nice. I throw it, I can tell exactly how it's going to go. I can't do that for a bat. It's rotating, it's spinning, it's going in a weird way. But if we actually trace a single point, a very special point in this bat, we will end up with this. That special point, which is not actually in the middle, but more towards the heavier side, traces out a perfect parabola, just as the ball does. So let's try and use a where's a video? There's supposed to be a video here somewhere. Oh, not this one. This one perhaps. There we go. Okay. Let's take a look at what happens when we're tossing something. Okay. We just threw something. We just threw something else. And it looks like they're going in all sorts of crazy ways. Now we're going to toss the exact same things again, but at this point, we're going to calculate the center of mass and we're going to paint it in orange, very bright orange, and we're going to see what it looks like in the dark. And I'm actually going to play this at a much slower speed so that we can take a look. See what happens. Do you see that? Look again. Once more. Take a look. The center of the object is going a perfect parabola. I'm going to stop this now and go back to our lecture. Okay. So what we just saw was this, what we call the center of mass of an object. Enough examples. Let's go back to the definition. So what is the center of mass? Without involving physics and mathematics, the center of mass is how an object would behave if all of its mass was exactly concentrated at that point. And we can take any solid object whatsoever and redesign it so that it behaves as such. We usually do something like this or see people doing things like this and we think of it as magic or something very, very smart. Take a look at this triangle. The ball is perfectly resting on it. This is not magic. This is simply the ball being put exactly where its center of mass is exactly on top of the triangle. I can do the exact same thing with a baseball bat, just like this. And it wouldn't fall down, it would go a bit like this and it's going to stick right horizontal. We can even have similar things with stuffed birds. The only important thing is the center of mass, the beak of the bird in this case, is perfectly aligned with the center of the cone. One last example is the reason why you don't fall down when you actually kneel. If you take any human being, the mass on the top half of your body is way more than the mass in the bottom half of your body. Your skull and your brain alone weighs a lot. So if this wasn't the case, as soon as you would kneel down, you would actually topple over. The reason you don't is because your center of mass is right here in the center. And I realize now it's not showing, so let's do this. There we go. See, your center of mass is exactly at the right position with your feet. So you're not falling down. If it was slightly shifted to the left or to the right, you would topple either to the front or to the back. Okay, what if I have more than one particle? What do I do then? Well, if I have more than one particle, say if I have one marble and a second marble, both are absolutely symmetrical and their center of masses are exactly in the center. What then? Well, I'm going to treat them as a system of particles. So two of them as one system, as one particle. If I do that, where is it going to be? Where is the center of mass going to be? If I attach both of these with a rope or something and I throw them together, how would it behave? Well, it would be right in the middle between the two, because they have exactly the same mass. So just like when we had that square, we do the exact same thing. Okay. What if we have a slightly bigger marble? Now the one on the right is heavier than the one on the left. So that center of mass is going to shift. Where do you think it would go? I say it would go towards the heavier bit of it, just like the bat. And voila. Now there is a precise mathematical formula to calculate where exactly the center of mass is going to shift. If we take the point 0 to be somewhere here, okay, now m1 for the ball 1, m2 for the larger ball, x1 to the center of mass of ball 1, x2 to the center of mass of ball 2. The way to calculate the center of mass is a formula that says m1 x1 plus m2 x2 over m1 plus m2. Okay. What if I have more than 2 particles? Say I have 10 particles. What then? What do I do? Well, we will have mi xi over sum of m. What does that mean? It means we take the mass of every single particle multiplied by its distance from the 0 point, add them all up, and then divide by the total mass of all the particles together. All right? Let's do a practical example. Consider the Earth and Mars in their orbit around the Sun. Where is the center of mass located for this 3-body system? Is it closer to the Earth than it is to either the Sun or the Mars? Center of the triangle that has all of them? Half the distance, is it right in between? Closer to the Sun? Closer to Mars? Where is it? Now, before we do the calculation, remember that it all has to do with mass and distance. Where is your 0 point? I'll leave this on the screen for a couple of seconds. I suggest you pause the video, try to figure it out yourself, and then resume the video if you don't know how to solve it. Okay. Here's the Sun, here is Earth, and here is Mars. Now, as you can see, the Sun is way bigger. So without even doing any mathematics, we can immediately say that it's closer to the Sun than either Mars or Earth. As a matter of fact, it's probably going to be somewhere here. Very, very close to the Sun. What if we have something in 3 dimensions, not only 1 dimension? Well, just like we did with vectors before, the x and the y and the z axes don't speak to each other. We can say RCOM instead of XCOM and take it all the way back to the origin, but then we can break that down into x, y, and z COM. The XCOM would be MIXI over M, the YCOM would be MIYI, and the Z would be MIZI. And overall, the R center of mass would be X in the I direction, Y in the J direction, and Z in the K direction, just like we did before. Let's take a look at this. This is a uniform square plate. Okay. Now, what happens if we remove any of those squares, 1, 2, 3, and 4? At the moment, the center of mass is going to be right in the center. What's going to happen if we remove some of those? Well, we start with the center. If we remove the square number 1, there's less mass on there and more mass near number 3. Number 2 and number 4 are still balanced. So the center of mass is going to move slightly towards the heavier side, the number 3. If we remove 1 and 2, now there is more mass down, so it's going to be still on the y-axis, but below the x-axis. If we remove 1 and 3, what's going to happen? I would say it stays in the center, because those two removes are balanced, and the 2 and 4 are still perfectly balanced. What if I remove all 3? I think by now you know the answer. It's going to go way near to 4. And if I remove all 4 of them, then it just goes back to the center. Let's do another example. This is an L-shaped rod. Okay. Both of them are of length L. Where is the center of mass of this L shape? Let's do it in a different way. Let's consider the shape to be made of two uniform rods, rod A and rod B. And they have exactly the same mass. And then we're going to plug it in. Well, the center of mass of rod A is going to be in the middle of rod A, and the center of mass of rod B is going to be in the middle of rod B. Just so. And we'll take the point where they intersect to be point 0. So let's make a table. Mass, X, and Y. Both of are of mass M. The center of mass of L1 is at L over 2, 0, and the center of mass of L2 is 0, L over 2, where L is the length. Now we plug it into our equation for the x-axis, we get L over 4, and we plug it into our equation for the y-axis, and we get L over 4 again. Let's do another sample problem. The reason we're doing so many sample problems in this course is because this is actually a difficult concept, and it's a new concept. So we need to do as many examples as possible, and I remind you to do the questions in the work plan. Those are very, very important to get you to understand the way the equations work in reality. This is actually an interesting problem. We have a circle, and we cut out a part of that circle. The circle has a radius 2r, and the small circle has a radius r, and we cut it out of the bigger circle. So now we have a very weird shape, and we want to know where is the center of mass of that weird shape. What do we do? Well, this is a bit more involved, so we're going to do it in steps. We're going to have the small circle, we're going to have the medium circle, and we're going to have the weird shape. The small circle is going to be called S, the big circle is going to be called C, and the weird shape is going to be called P for particle, or whatever you want. Where is the center of mass of S? Right in the middle of S. Where is the center of mass of C? Right in the middle of C. Where is the center of mass of P? We don't know where exactly, but we know, just like on the square example, when we remove the part of the square on one side, it shifted to the opposite side. So since we removed the circle from the left, we expect it to be the center of mass to be shifted to the right. Okay. Let's now do some maths. Here's my x-axis, here's my y-axis, here's my 0 point. I will have my 0 point go right through the circle, and then I'm going to be removing my small circle, and then I'm going to be having my weird shape centered right at 0, 0. Okay, now what do we do? Well, let's look at masses. The mass of the P is MP, mass of the small circle is MS, mass of the medium circle is MC. We know these are the center of masses points, approximately. Let's do some maths. I'm going to write down all the distances. Okay, let's look at the plates, P, S, and C. Center of mass, I'm just going to call them COM-P, COM-S, and COM-C. Where's the location of the COM? Well, for C, it's at x equals 0. For S, it's going to be at x equals minus r, as we see in the diagram. And for P, it's going to be positive. We just don't know how much. What's the mass? Well, mass of C, the full thing, is the mass of S plus of the mass of P. The mass of S is just the mass of S, and the mass of P is just the mass of P. Simple mathematics. My XCOM is M1x1 plus M2x2 over M1 plus M2. I substitute it in. My XC is MSXS plus MPXP over MS plus MP. So far, that's fine. Let's put in those numbers. XC is 0, XS is minus R, XP is, we have a problem. We don't know what it is. That's fine. We simplify all the mathematics and we get XP equals minus XS MS over MP. Now we have a tiny problem. We do not know the mass of MS or MP. Or MC even. Well, we know it as MS plus MP, but we just don't have a number. So what do we do with that? Well, we know that mass equals density times volume. Let's use that. What's volume? Thickness times area. So MS over MP equals density times thickness times area of S over density times thickness times area of P. So far, so good. Now, thickness of S and of P are the same, and the densities are the same because they're made of the same material. So these just go down to 1. We only have area S over area P. Area S stays on the top. Area P is simply area C minus area S. Now we put in some numbers. Pi r squared for S, pi 2r squared minus pi r squared for C and S, and we get 1/3 for MS over MP. Now when we put it back in, we have XP equals minus XS over MS over MP. MS over MP is 1/3, and we get XP is now at 1/3R. So it indeed moved slightly to the right. Let's take another look at 3 dimensions. We have 3 marbles in 3D space. So they're at locations R1, R2, and R3. R is simply XCOM plus YCOM plus ZCOM, each in their IJK directions. So RCOM is MIRI over all the M's. I call that MIRI. MIRI over M. Let's do a comparison. In one-dimensional, XCOM is MIXI over M. In 3D, it's MIRI over M. How do I find velocity? Well, If I want to find the velocity of the center of mass, I simply need to look at how the center of mass is moving. If I know what is my RCOM, my position of my center of mass, I just need to see how fast, how much is it moving with respect to time, and I have VCOM. What about acceleration? I do the exact same thing, but with velocity of COM, which is what we have been actually doing all along. Every time we have been just using a single point for all of these things, we have been taking it as the center of mass. And if I multiply that by the total mass, I get the force. Let's take a break and come back in a little bit. And we're back. Okay, this is part 2 of the beginning of chapter 9, which is a very, very long chapter. So I split the recording into 2 parts. So let's start it with the PIQ, sort of a revision and sort of an application. If we have 2 different balls, okay, ball A of mass m moving to the right at a speed of 2v, and ball B of mass 3m moving to the left at speed v. Before the 2 balls collide, what is the magnitude and direction of the velocity of the center of mass of the system? Well, first thing first, what do we need to find? Let's draw it out. This is m, this is 3m, this is going 2v, this is coming v, and the center of mass is going to be somewhere here in the middle, but closer to the heavier object. We know this so far. Now, how do we find the center of mass? Well, as we said before, for v, it's going to be exactly the same formula as for r or XCOM, only instead of the x's, we're going to have the v's. So let's put it in. So instead of m1x1 plus m2x2, I have m1v1 plus m2v2 over m1 plus m2. Put in the numbers, and we get minus v over 4. So on average, the center of mass of this thing is moving to the left. Let's now look at Newton's second law again, but this time instead of one particle, we're looking at a system of particles. So this time, we're going to be looking explicitly at the motion of a system's center of mass. What do we see? Well, F is still equal to ma, but now instead of just a for a particle, it's going to be for the system of particles. So instead of a, we're going to have ACOM, a center of mass. As with the velocities, as with the accelerations, as with the centers of mass, as with the positions, x, y, and z do not speak to each other. So ma com x, ma com y, and ma com z are independent of each other. F net is the sum of all the external forces. The word external is very important. M is the total constant mass of the entire system. And ACOM is the center of mass acceleration. How do we use it? Let's look at this. 3 particles are initially at rest. They're not moving. Each experiences an external force due to the bodies outside the system. The directions are indicated. One is F1 like this, one has F2 at 45 degrees, and one has F3 to the right. And the magnitudes are also given. F1 is 6 newtons, F2 is 12 newtons, F3 is 14 newtons. What is the acceleration of the COM? And where does this whole body move? Well, F net equals ma com. So we need to find F net to start with, and then we need to figure out a com. So a com equals F1 plus F2 plus F3 over m. Simple rearrangement. And now let's do it in x-axis alone and y-axis alone. All the f-axis, add them up, divide by m, you get a com. All the Fy's, add them up, down, divide them by m, you get a comma y. What is my a comma? We find the magnitude of that acceleration, and for that we find the modulus. So a comma x squared plus a comma y squared, and then square root that, and we get about 1.2 meters per second squared. It's positive, so it's to the right. Okay, how much to the right? Well, we find the angle theta. Tan inverse of a comma y over a comma x gives us about 27 degrees. So this is our a comma. One more example. Girl sitting in a boat. A girl is sitting at the front of a boat on a still sea, so it's not moving. The boat is not moving, it's at rest, and the front of the boat is pointing north. The girl starts walking to the back of the boat. What is the F external on the system? The system is sea, girl, boat. And then the question says, as the girl moves south to the other end of the boat, the center of mass of the system, will it move or not? And the last bit is, as the girl moves south to the other end of the boat, what will happen to the boat? Okay, so the girl is at one end of the boat and north is to the right. She starts moving and now she went to the other side. Now what will happen is the boat will move north of its original position. While the girl is going this side, the boat will move to the other side. Okay. What's going on? Well, let's take this point as a reference line. Okay, and this is where the girl is, and this is where the x-com of the girl is. Okay, and this is where the x-com of the boat is. Now what's happening is that when you take the x-com of the entire system, girl plus boat, it's somewhere in the middle between the boat and between the x-com of the boat and the x-com of the girl. Now, as the girl moves to the other side of the boat, the x-com overall moves closer to where the girl is. Okay, because it's the other way around. Instead of the x-com of the boat here and of the girl here, the x-com of the boat is still here, but that of the girl is all the way on the other side. And that causes the boat to move. As for the rest of the questions, I will leave it again on the screen for a bit. Take your time, do them. We will release those questions on Google Classroom, and then later on we'll give you the solutions to them as well. Okay. What is the importance of the center of mass? The center of mass only changes if there is an external force. If the forces are only internal, the object will behave as if the center of mass is still at the same place and everything else will accommodate. Take, for example, some fireworks. You fire them from one place, they go in an arc, and then they explode. Once they explode, the tiny pieces go in all sorts of directions. But no matter where they go, if you use strong enough computer and do the calculation, you will see that the center of mass will keep going into a parabola and down to the ground as if nothing else happened. Okay, and this is very important in things, for example, like airplane crashes. One of the ways that investigators figure out whether the airplane was hit from something like a missile from the outside, or if there was something like a bomb on the inside, how do they figure it out? They track the center of mass of the plane after it falls down. If the center of mass doesn't tally by what was going on before the explosion, they know the explosion was not from inside the airplane, it was from outside. I will leave this again for a few seconds for you to take a look at. And I'm actually not going to do this problem in detail here. I am going to leave it to you to do. And once I post the slides to Google Classroom, you can then follow through and see if you can do it. If not, you can always email me back. Okay. Now here's a question. This is the last thing we're going to be doing today. Say, for example, you have an accident between two small cars. What happens? Now you have the same accident, but between a big car and a small car. What happens? The result is very different. In both cases, both cars might be going with the exact same speed, and the accident would happen in the exact same way, but the result would be very, very different. Why? Well, this brings us to the idea of linear momentum. What is linear momentum? Say, for example, you have this dog, which is going, it has a mass m, it's going with a velocity v in this direction. The linear momentum, we use the small letter p, and it's a vector, is defined as the product of its mass times velocity, mv. P equals mv. Okay. Units, kilograms, meters per second, otherwise known as Newton seconds. Why is it useful? What do we do with it? Well, momentum is a vector quantity with a direction same that of velocity, but it also takes into account the fact whether something is big or whether something is small. Okay. Remember when we were talking at some point in the previous lectures about the truck and the butterfly, and we had a lot of problem understanding that although the force would be the same, how could it be? Because the butterfly is very small, the truck is very big, and we had to invoke the idea of mass. Yeah, that because one mass is very small, the acceleration is going to be very big, or the mass is big, so acceleration is going to be small. Now, all of this can be summarized in the idea of momentum. Okay. And the linear momentum of a system of particles, since it's a vector, we simply add them up as vectors, just like we do with forces. m1v1 plus m2v2 plus m3v3 all the way to the end. And for a system of particles, we simply do total mass by v-com. Done. Okay. What about the rate of change of momentum? How quickly the momentum changes? Okay. This brings us back to the idea of, the butterfly and the truck. The rate of change of momentum is it's dp by dt. M is a constant, so it goes out. So we get m dv by dt. And what that is simply ma-com. What is ma-com? Force. Right? So remember when we said the force on one is the same as the force on another? Because the rate of change of momentum was the same. So this figure gives the magnitude of the linear momentum versus time for a particle moving along an axis. A force directed along the axis acts on the particle. We want to rank the four regions according to the magnitude of the force. Biggest first. Which one? Well, this is momentum. Force is rate of change of momentum, so dp by dt, which is slope. Biggest slope, number 1. Second biggest slope, number 3. Number 2 and number 4 have 0 slope. Correct? So in order, we have 1, 3, and then 2 and 4 are equal. In which region is the particle slowing down? Well, in region 3, because the momentum is decreasing. P equals mv. M is a constant. V is decreasing. With this, we come to the end of today's very, very long lecture. I hope it was useful. As usual, any feedback is welcomed. And I will see you again in the next lecture. Have a good day.